Moving on to continuity. So yeah, continuity. Let's look at some examples. So here's a function, f of x equal to, and I'll point out most of our examples of functions that have questionable continuity are piecewise. We'll talk about all the things, but we'll start with this. Let's look at it. We got f of x equal to x squared when x is less than 2, and it's equal to x plus 2 when x is greater than 2. Graph it. Things are happening at 2. So it's equal to the nice good old parabola, x squared to the left of 2. And if we plugged into 2 squared would be 4. So it looks something like this. And then to the right, it would look like the line y equals x plus 2. But we can see that this function isn't continuous at 2. So I'll point out f of x is not continuous at x equal to 2. Welcome. Change this up here real quick. Andrea, when you have a second, if you could please fill out the attendance form, that'd be great. And specifically, not continuous at 2 because f of 2 is undefined. Right? This function isn't even defined to be anything when x is equal to 2. So it certainly can't be continuous there if it's not defined there. And there, you can probably all see this field. There's a little open hole right there at the point 2 comma 4. I would point out that if you were drawing this, you can just set it down. You can leave it, that's fine. Or you can pass it. Did everyone get the attendance form? Pass it back around. So you would technically have to lift your pen up off the paper to jump over that little hole right there, which is often the way we talk about continuity graphically, is that a function is continuous if you can draw it without lifting your pen or pencil off the paper. And it's not otherwise. So here, technically, there was a little jump I had to make to go there. And that would be true whether the function was undefined there. Let's actually, we'll come back to that. Interesting, yeah. So let's look at this second example, where we're now going to have, it's going to be similar, except now it's going to be equal to still x squared when x is less than 2. But now it's going to be equal to x plus 3 when x is bigger than or equal to 2. So a couple of things are happening there that differentiate this piecewise function from that one. We still have the same left part. And then when we get to 2, well, we're still having a hole at 2 comma 4. And then if we try to graph this other piece of the piecewise function, well, if we plug in 2 for x, 2 plus 3 is 5. So this straight line part to the right starts a little higher. I think we can all look at this and agree, yeah, that doesn't look like something that's continuous, right? We drew it and we had to lift our pencil off the paper to draw it. The way you would say this isn't continuous is, well, if we look at the limit from the left, the limit as x approaches 2 from the left of f of x is equal to the limit as x approaches 2 from the left. We're going to use the left piece, which is x squared. If we plug in 2, we get 2 squared, which is 4. On the other side, we approach 2 from the right. We end up getting the limit as x approaches 2 from the right of x plus 3, which is 2 plus 3, which is 5. And since those two limits aren't matching up, the limit doesn't exist. So we would say here that f of x is not continuous at x equals 2. Not because it's undefined, because it certainly is defined. F of 2 is equal to 5, but because the limit doesn't exist. Limit as x approaches 2 of f of x does not exist. The right-hand side and the left-hand side aren't going toward the same place, which certainly means we can't have continuity because there's going to be this jump from a value of 4 on the left to a value of 5 on the right. Can I make this last one fit in here? It's dicey. Let's not. So let's look at this third example where we're going to kind of combine. Well, we're actually going to take this first example and just change it a little bit. So we're going to say that we now have f of x equal to x squared when x is less than 2, 7 when x is equal to 2, and x plus 2 when x is greater than 2. So if you want to make your life easy, instead of graphing this one again, you could just take that graph and plot the point 2, 7. I'm going to graph it again because I should. Sure. Here's our parabola on the left. We're looking at the best parabola I've ever drawn. Here's our line on the right. And here's 7. I'll point out that if I was drawing this from left to right, I would have drawn the parabola. I would have jumped up to that point there. And then I would have continued on back to. I think, again, visually, this doesn't look continuous, right? We couldn't just draw it all in one go. So here we have, well, I'll say that 1, I won't remember this. I'll point out that f of 2 exists. It's equal to 7. The limit as x approaches 2 exists. I should say limit as x approaches 2 of f of x exists. It's 4 from the left, it's 4 from the right, so the limit is 4. But those values aren't equal to each other. And since they're not the same, we end up getting this jump here. I should really say it's not a jump discontinuity, it's a point discontinuity. The previous one was a jump discontinuity. But since we have this removed point, this function is not continuous. So here, f of x is not continuous at x equal to 2, because although the limit exists and the function exists, they're not equal to each other. Because the limit as x approaches 2 of f of x does not equal f of 2. So this kind of leads to our definition of continuity at a point. And I would say, although really we can write the definition as just one thing, it's actually more easily applied as a 3-part definition, which kind of include all 3 things here. So here's what we're going to say. Keep things on the board here. So definition. Sure. F of x is continuous at x equal to a if and only if the following 3 things are true. 1, f of a exists. 2, the limit as x approaches a of f of x exists. Usually this means the left side and the right side. Yeah, usually this means checking the left and the right hand limit. So often this means checking the limit as x approaches a from the left of f of x is equal to the limit as x approaches a from the right of f of x. Thirdly, and most importantly, they have to be equal to each other. The limit as x approaches a of f of x has to exist and be equal to f of a, which also has to exist. I will point out that really you only need to say the last thing. This last thing, for the limit to be equal to the function value, encompasses the fact that they both have to exist. If the limit didn't exist and the function didn't exist, we wouldn't say, oh, it's continuous because the not existing equals the not existing. We would just say, yeah, it's not continuous because nothing went right. So most books will write the definition as just this last part here. But I think it's easier to kind of test for continuity if we apply these three things to make sure that we've checked all the things. Questions about that? Yeah.
For the limit and the F
This one here?
Yeah. Since we have limit as x approaches 2 and just 2, not 2 from the left or from
Right.
the right, why didn't you pick this 7 that is equal to 2?
Well, because the limit says, and so let's actually take a look here. So we look at the left-hand limit, the limit as x approaches 2 from the left. All right, if we're left of 2, are we using x squared, 7, or x plus 2?
X squared.
Right. And then as x gets closer and closer to 2, x squared gets closer and closer to 2 squared, which is 4. And on the other side, the limit as x approaches 2 from the right. Now which piece are we using? Oh, x plus 2, right. And then we're going to plug in the 2 and get 2 plus 2, which is 4. So again, I want to make it clear, or I want not just make it, I want to say it again because I say it a lot. When we talk about the limit as x approaches a number, we care what's happening really, really close to that number, but not actually at that number. So we don't care that at 2 the function is equal to 7 when we're talking about the limits. We care that as you get closer to 2, the corresponding y values get closer to 4. And that's true on either side of 2 in this example. But you've kind of precise to hit upon the difference between talking about a limit and talking about continuity. When we're talking about continuity, we care both about what the limit is, what the y values are getting closer and closer to as x approaches that number, and what the y value actually is at that x value. Yeah.
Would the limit exist if x was less than or equal to 2, or if
So in this third example here, the limit does exist. The limit is equal to 4, but the function is not continuous. And actually, that's a really good point as well, because I've seen many students over the years stop at this second part here and say, oh, the limit exists, we're done. Because often we are, but not always. There are lots of functions where the limit ends up existing and the function actually doesn't have continuity there. Let's look at a couple of examples. We'll talk more generally here. Oh, here's a great example. Let's say our function was equal to, sure, sine of 2x over x if x is not equal to 0, and 3 if x is equal to 0. And yeah, we'll have to stop. We'll have to pause and say some things in a minute about this quotient here. But for now, I'll just point out sine of 2x is continuous everywhere. So is x. And their quotient is continuous everywhere as well, I should say everywhere it's defined. And that's just, and you know, we'll take a minute here to talk about the kind of rules for when combinations of functions are continuous or not. But for now, bear with me to be like, okay, yes, this function is continuous, except for maybe it's 0. And it's certainly not defined at 0, because if you plug in 0, you get 0 over 0. Okay, so let's talk about all three things. Now, I should say, that piece of the function is undefined at 0. The function itself is well defined at 0. I have defined it to be equal to 3 when x is 0. So let's check to see, is f of x continuous at 0? Continuous at x equal to 0. So we're going to check three things. First thing, does f of 0 exist? Yeah, it does. F of 0 is equal to 3. There's not really a lot of work to do there. We just look at the piecewise function and say, oh, they said the function was 3 when x was 0, so that's what f of 0. Now the second part. Now, in this case, we're not going to have to use it one side. We're not going to look at both one-sided limits, because whether x is bigger than 0 or x is less than 0, the function is defined to be sine of 2x over x. So we're just going to look at the double-sided limit as x approaches 0, because on either side of 0, we have sine of 2x over x. Now, I know it's been a little while since we talked about limits like this, but we definitely have talked about limits like this, where you have sine of something over something, and something's going to 0. We want the denominator to look like the argument of the sine function. So I'm gonna wish for what I want. I have sine of 2x divided by x, and I wish I had a 2x beneath my sine of 2x, so I'm gonna make it happen. Wishes come true. There's my 2x. But I can't just divide by 2x, I also have to multiply by 2x. So then if we simplify, the 2x divided by x is just 2. And the limit as x goes to 0 sine of something over the same something that's going to 0 is 1. That's going to be 1. That's going to be 2. And we're going to get 1 times 2, which is 2. Great, the limit exists. The function exists. But they're not the same. So the limit, in fact, instead of writing this next part, what I would really write is, I already know what's going to happen, right? I know it's not going to be continuous. So the words I would actually write are, we see that f of x is not continuous at x equal to 0 because the limit value, the limit as x approaches 0 of f of x is equal to 2, and that's not equal to the function value at 0, which is 3. This is an example of a point discontinuity, or there's a different word, a removable discontinuity, in that we could fix it by moving one point. In fact, let me show you what I mean. I can just graph it. I'm not that bad at graphing, probably. So here is kind of what the function looks like. Sine of 2x divided by x, well, we just said the limit was 2. So 1, 2. Bear with my not excellent drawing here. Sure. Sorry, I'm thinking about what's that's. Yeah. It looks vaguely like this. And it's symmetrical on either side. So it looks kind of like that. And then we've defined it to be equal to 3 when x is 0. So there's the function that we actually just showed was discontinuous at x equal to 0. I'll point out it is continuous everywhere else. So if someone asked this question, instead of asking it as is f of x continuous at x equal to 0, a more common way of asking a question like this is, where is f of x continuous? It's kind of like asking for the domain of a function, in that usually we find the answer not by finding all the places where it's continuous. We find the answer by finding all the places it isn't and then saying it's the rest. So here, this function is continuous everywhere except for x equal to 0. So we say it's continuous on the interval from negative infinity to 0, exclusive union 0 to infinity. I would also point out that we could make it a continuous function if we wanted to. So although this function isn't continuous, yeah, I'm going to squeeze it in here, even though I feel slightly bad about it, but not that bad to not do it. Note that we could write this function, we could make a new function, g of x equal to sine of 2x over x when x is not 0. And instead of making it equal to 3, make it equal to 2 when x is 0. And this function is continuous everywhere, including 0. Let's say from negative infinity. Why is it flickering like that? Sorry, to infinity. Maybe there's a loose connection over here somewhere. So there's an example of what we call a point or removable discontinuity, which can be fixed, or I should say made continuous by moving one point up or down to fill in the hole that was there. Cool. I try not to say any questions, because if you have questions, you should just ask them. But if you have any questions, you just ask them. So let's look at not an example, but talk about a few things that are continuous everywhere. And I think some of your instructors probably all said this, but let's talk about.
One quick question. If we're like asked the question in the way, where is f of x continuous? How do we know we should pick 0?
Well, so typically in a piecewise function, that's actually a good question. How do you know what the candidates are for lack of continuity? Well, in the piecewise function, anywhere you're changing from one piece to another piece is automatically a candidate for we might not be continuous there. And then the other things that might pop up are places where the function looks like it could be undefined. So to that end, let's talk about what kinds of functions are continuous where. The blanket statement I'm going to make, yeah, in fact, I'm going to write stuff first. Is so just here's the general rule of thumb. Most, which I know is not very specific, most functions, most normal functions, are continuous on their domains. Meaning, if they're defined, they're continuous there. There are some exceptions to this, but they're few and far between. Kind of have to work hard to make a function that's defined somewhere and not continuous there. Like the previous example. The previous example was defined at 0, but it was not continuous at 0. That's kind of atypical. In fact, you'll see most of the examples you have of discontinuity are going to be from piecewise functions because it's just hard to make it up otherwise, to be perfectly honest. But here's kind of a more specific guideline. Polynomials are continuous everywhere. So what makes a polynomial a polynomial? Powers of x are non-negative and integers. So for example, like f of x equal to x cubed plus 1, or g of x equal to 2x to the 7th plus pi x squared minus 3, or h of x equal to 5. All those are polynomials, even the last one that's kind of boring. The last one is a 0th degree polynomial because you have x to the 0th power that we didn't write. But all these are polynomials. They're defined everywhere, right? We don't have any domain issues. There's no division by 0 or even roots or logarithms. So continuous on its domain, and its domain is everything. Okay. What else? Rational functions. The rational functions, which are just polynomials divided by polynomials, are continuous on their domains. And really, I could have said that for the previous one because every polynomial has a domain that is every real number. I'm going to amend that. So for example, f of x equal to x squared plus 2x plus 3 over x squared minus 16 is continuous everywhere except for what values of x? What's one problem value? What's the other one? Yeah, -4. So this is continuous on the interval from -infinity to -4, union -4 to 4, union 4 to infinity. As long as a rational function is defined, it is continuous, but if it's undefined, it can't be. And typically what this means is you have vertical asymptotes at those places where it's undefined. Although technically you have to do a little bit more inspection to see if it's a vertical asymptote or a hole, but that's not the point right now. Trig functions. Every trig function defined, or sorry, continuous on its domain. So I'll separate them into two different groups. Sine and cosine are extra special. Sine of x and cosine of x are continuous on their domains, which is everywhere. Continuous, gosh, that was a word I have to spell. Everywhere. Hopefully you have a good image of what those graphs look like in your head. You can be like, oh yeah, that thing doesn't break anywhere or have a hole or do anything funky. It's just doing the sine thing or the cosine thing forever and ever and ever. The other four functions, secant of x, cosecant of x, tangent of x, and cotangent of x. Although it feels weird to say it because if you look at them, they don't feel continuous, but they technically are continuous on their domains. Continuous on their domains. Now, their domains are annoying, right? For example, if you look at f of x equal to tangent of x, which is really equal to sine of x over cosine of x, that's going to be undefined whenever cosine is equal to 0, which is any odd multiple of pi over 2. So we could say this is continuous, but annoyingly, it's continuous on this domain. So I'm going to write this out, but it's going to be not pretty. So it's like dot, 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 and then we have like negative 3 pi over 2 to negative pi over 2 exclusive union negative pi over 2 to pi over 2 exclusive union pi over 2 to 3 pi over 2, and it just goes on and on and on. But again, if we're asking about where a function is continuous, well, tangent's continuous as long as it's defined. And it's only undefined at pi over 2, and 3 pi over 2, and 5 pi over 2, and 7 pi over 2, and so on and so on. What are we missing? What other kinds of functions are there? I can think of 2.
Piece function.
Say that one more time.
Piece function.
Piecewise functions are kind of the special outliers. I'm thinking of, what am I thinking of? Oh, I know what it is. Exponential functions. So f of x, the most common one you're going to see is e to the x, but really any base that is positive and not 1. Continuous everywhere. And the last one I can think of that comes up, oh yeah. Yes, exactly. That's the last one I was going to think of. F of x equal to the natural log of x, or really any logarithm, log base b of x, with the same restrictions, in that your base should be positive and not equal to 1. Why not 1? Well, because 1 to the x isn't really an exponential function. It's just 1 to any power is always 1. It's a constant function. And why not 1 here? Well, log base 1 of anything is going to be problematic. It doesn't usually exist. So this is also continuous on its domain. Now the domain of the logarithm is much different, right? The domain here is every positive number from 0 onward. And is there anything else on my list? Nope, I think that's it. So these functions are continuous on their domains, and then their combinations are. So basically, combinations, which I know I'm putting in quotes there, of continuous functions are also continuous. When we say combinations, I'm thinking of the following kinds of things. So more explicitly, if f of x and g of x are continuous, we could say either continuous everywhere or continuous on the same domain. I'm going to say the same domain because it's a little more specific. Then so are the following. F plus g, f minus g, f times g, f divided by g, as long as g isn't equal to 0. So basically any any arithmetic manipulation you can do where you're adding the functions, subtracting the functions, or multiplying the functions, dividing the functions, or squaring the functions, or cubing the functions, or doing anything like that, the functions are still continuous on the same domain. So for example, h of x equal to sine of x plus e to the x plus x cubed plus 5. Well, since each of those functions on their own are continuous everywhere, this combination, this sum of continuous functions, is also continuous everywhere. Continuous on the interval from negative infinity to infinity. Or for example, f of x equal to cosine of x plus 2 to the x over x cubed minus 1. It's continuous almost everywhere. Cosine's continuous everywhere, so is 2 to the x, so is x cubed minus 1, but we do have to worry about x cubed minus 1 being equal to 0. So this is continuous as long as x isn't equal to 1. This is continuous on the interval from negative infinity to positive 1, union positive 1 to infinity. So I'll say it again with feeling. Most functions are continuous on their domains, meaning as long as they're defined, they're continuous. The usual exception to this are piecewise functions. Those are the majority of our examples of functions that are going to be discontinuous. Yeah. Let me give you an example of one that you might say, James, that's not piecewise, and I'll be like, yes, it is. Let's say we have, let me think something here. So we have f of x equal to, trying to think about something kind of interesting here. The absolute value of x plus 2 over, that's not going to work out so well, James. Sorry, I was trying to think of something funky and fine, we'll just deal with that. The absolute of x plus 2 over x plus 2. Definitely not going to be continuous. Definitely not continuous in -2. So it's not continuous at x equal to -2. I'm curious though what it's equal to otherwise. So let's kind of look at this function a little bit more in depth. Do I really want to look at this? I really don't want to look at this more in depth actually, because I kind of made it something weird. So I'm not going to, even though I kind of set you up for not a great example there. Apologies. Sometimes when you think of stuff off the top of your head, it doesn't come out great. But I will point out this function is continuous everywhere else. From negative infinity to -2, union -2 to infinity. I'm kind of curious what this looks like, but not curious enough to deal with. A little curious, but not that curious. I would encourage you all to graph this on your own using Desmos. Check it out, see what it looks like. I think you have a vertical asymptote at -2. Yeah, I'm pretty sure. Yeah, we do, right? Because so let me ask you, okay, fine. Convince myself. If you plug in -2, what do you get? Well, clearly we get division by 0. What do we get on top? 4. And we know that when we have a non-zero over 0, that limit's going to be like if we actually try to find the limit as x approach -2, we get some sort of either positive infinity or negative. And I think they both be, actually, I think you're going to get one of each. So if we take the limit, the x approach is -2 from the right-hand side of the absolute value of x plus 2 over x plus 2. Well, the top is clearly going to be positive 4. And the bottom, since we're a little bit bigger than -2, like -1.9, -1.9 plus 2 is slightly positive. So we're getting positive infinity. On the other side, if we approach -2 from the left, the numerator is still positive 4, but now the denominator is slightly negative. So we get negative infinity. So this has some funky asymptote thing going on. Okay. So let's look at some more piecewise examples, because that's where honestly you're going to see on an exam, most of the time you're going to ask questions like, where is this function continuous or not continuous? There's that's one of the styles of continuity questions. There's another one which we'll get to as well. So let's look at this example. And I'm going to ask it in the way I think is more annoying. Where is the following function f of x continuous? So where f of x is equal to 6 over x plus 2 plus e to the 5x when x is less than 0. 4 times cosine of pi x when x is bigger than or equal to 0 and less than or equal to 1, and it's equal to x to the 17th plus the cube root of x plus 6 when x is bigger than 1. And when you see this question, you really should be asking the negation of that. Where is f of x not continuous? And then your answer is great everywhere else. Let's first look at each of the pieces and see if they might be discontinuous anywhere on their own. So looking at this bottom piece here, x to the 17th power is a polynomial, good to go there. We didn't really talk about roots, and I suppose I should have. So yeah, in fact, I really should have. So back to add to our list, root functions like the cube root of x, the square root of x, the fifth root of x are continuous on their domains. I know, surprise, surprise. But the domains differ depending on whether the root is even or odd. So just a quick aside over here. Yeah, we have. So f of x equal to the nth root of x is continuous on the domain. Continuous on, and the domain is different depending on whether n is even or odd. So it's going to be all non-negative numbers if n is even. If you have a square root or a fourth root or a sixth root, it's only defined for non-negative values of x. But if you have an odd root, then the function is defined and continuous everywhere. So the cube root of x is a function that's defined everywhere, which is nice. So just to make sure everyone's clear about that, you can take a cube root of a negative number. You can take a fifth root of a negative number. It's not always pretty, or just like a square root isn't always pretty. What's the square root of 2? I don't know. Nobody actually knows. It's approximately 1.4, but it's not very nice. In the same sort of way, you can take a cube root of -8 and get, well, not approximately, actually equal to -2. But you could also take the cube root of -3. And although it's not a nice number, it is a real number. There's an actual real negative number that if you multiply it by itself 3 times, it equals -3. I don't know what it is. It's -1 point something, but it's a real number. It exists. So you can always take a cube root, fifth root, seventh root, 1,001st root of a negative or a positive number. Not true for even roots, right? Even roots, we can only take even roots of non-negative numbers, right? 0 and anything positive. And again, they're not always nice. Square root of 2. Okay, back to this though. This bottom thing is good to go. It's defined everywhere. We're cool. This middle thing, 4 times cosine of pi x. Cosine is continuous everywhere it's defined, and pi x doesn't have any problems, so good to go there. This first piece though, 6 over x plus 2 plus e to the 5x. The 6 over x plus 2 is undefined when x is equal to what? Right, and -2 is in this part of the domain, so this function actually is undefined at -2. So right off the bat, we can see that f of x is not or is discontinuous at x equal to -2. Now I'll point out, if we had switched the domains, like if we had said it was this bottom piece when x was less than 0, and this middle piece and the same part, and this last piece when x is bigger than 1, then we wouldn't get to say it was discontinuous at -2 because the -2, it wouldn't be defined to be equal to -2 on that part of the function. So make sure that the places where you're saying it's undefined are actually in the domain you're looking at. And then we should, of course, check what other 2 values of x. Right. Wherever you change from one piece of a piecewise function to the next piece of a piecewise function, there's always an opportunity to have some sort of jump or hole or whatever. So we should always check the places where we change from one piece to the next. So let's look at x equal to 0 first. And I like to show all the work I can. So here's the work we should show. Step 1, f of 0, plug it into the piece it belongs in, which is the middle piece, where x is defined to be equal to 0. That's going to be 4 times cosine of pi times 0. Cosine of 0 is 1. 4 times 1 is 4. Second part, the limit. Okay, so technically you really only have to check the limit from the other side using the piece we didn't already use. Because we already know that if I do the limit from the side of x where we're on the right side of 0, I'm going to use this piece of the function and get the same value. So the limit as x approaches 0 from the right of f of x is just the limit as x approaches 0 from the right of 4 cosine of pi x. And then we know we can plug in 0 and get 4. That's not the question. The question is whether the other side is going to match or not. So the limit as x approaches 0 from the left of f of x, we're going to use the piece of the function where x is less than 0, which is 6 over x plus 2 plus e to the 5x. We plug in 0, we get 6 over 2 plus e to the 0, which is 3 plus 1, which is 4. Hooray! So the limit exists, and it's equal to 4, which is equal to the function value. So we can see that f of x is indeed continuous at x equal to 0 because the function exists, the limit exists, and they are the same. So because the limit as x approaches 0 of f of x is equal to 4, which is equal to f of 0. Every time I've written a problem like this, one of the places where they change, it's been continuous. One of the places where they change, it's been discontinuous. It's not to say that's a guarantee, but it's often the case that if you've done one of them, it's continuous, you can probably expect the other changed place to be discontinuous. You still have to check and show your work, but that's what we're thinking is going to happen. And you don't have enough room. I need more room. Sorry, trees. So let's do x equal to 1. You might want to see the function though. This is one of the plantier podium things I've ever used. Oh well. So x equal to 1, same deal. We're going to check f of 1, plugging in 1 to the piece we need to. So that's going to be 4 times cosine of pi times 1. Cosine of pi is -1 times 4 is -4. Step 2, the limit part. So again, the limit from the left side of 1 should give us the same value. So the limit as x approaches 1 from the left of f of x is equal to the limit as x approaches 1 from the left of 4 cosine of pi x, which is just going to be -4. On the other side, the limit as x approaches 1 from the right of f of x. So now we're using this last piece of the function. So we're going to get the limit as x approaches 1 from the right of x to the 17th plus the cube root of x plus 6. And if we plug in 1, we get 1 to the 17th plus the cube root of 1 plus 6, which is 1 plus 1 plus 6, which is 8. Which is for sure not equal to -4. So I always think it's a good idea to, in addition to saying that the function isn't continuous at somewhere, say why it's not continuous. So it's either not continuous because the function didn't exist there, oh, but it did here, or because the function isn't equal to the limit, or because the limit didn't exist. And in this case, it's because the limit doesn't exist. So here we can say f of x is not continuous at x equal to 1 because the limit as x approaches 1 of f of x does not exist. Specifically, the left hand and the right hand limit are not the same. So there are two values of x where this original function is not continuous. X equal to 1 as we just showed, and x equal to -2 as we observed before. But it is continuous everywhere else. So if you like, you can draw a little number line. You don't really have to, but I'm just putting those numbers on there to remind me that, okay, great. I want everything else. I don't want -2. I don't want +1. My domain consists, my interval of continuity consists of every other value of x. So here we're going to say f of x is continuous on the interval -∞ to -2, union -2 to 1, union 1 to infinity. Oh, sorry, thank you. All right, question.
In this case, although one is not part of the interval community, one is part of the community.
Correct. That's an excellent point. So here's an example of a function, a piecewise function, not surprisingly, where the function isn't continuous on its domain. There's a place where it's defined, one specifically, where it isn't continuous. And again, I'll reiterate, these are almost the only examples of functions that are not continuous on their domains. It's really hard to make up a nice, like a regular function where it's just like f of x equals a thing that's not piecewise. Like I really literally actually cannot think of a function where it's just a nice not piecewise function and it's defined somewhere but not continuous there. It's really like it's really actually I'm like, can I think of one right now? Nope, I really can't. Nope, not that either. It's really hard to make one up. So most of the time, as long as the function is defined somewhere, and by most of the time I mean literally every time I could ever think of in my entire life, it's probably going to be continuous there, as long as it's defined. So let's look at this next example. Sure. So here's another example of a similar-ish kind of situation. So I'm going to give you the following one. F of x is equal to x squared plus 4x minus 12 divided by x minus 2 when x is not equal to 2 and 3 when x is equal to 2. And I want you all to do the work. So the question is, so the actual question is, where is f of x continuous? But the real question you're answering is f of x continuous where? What's the only point of concern? 2. Right? That's the only place where you're actually worried it's not continuous. So your job is to figure out, is f of x continuous at 2? So check the 3 things. Find f of 2, find the limit, and then ask yourself, are they equal? Now is your moment. Get to work. I'll give you a couple minutes to work on that. All right. Then 2. So f of 2, 3. That's it, right? There's nothing else to do with that. Limit as x approaches 2 of f of x, that's going to be the limit as x approaches 2, right? We're getting close but not equal to 2. So we're not using the piece of the function where x is equal to 2. We're using the piece of the function where x is close but not equal to 2. So it's limit as x approaches 2 of x squared plus 4x minus 12 over x minus 2. To no one's surprise, if we plug in 2, what happens? We get 0 divided by 0, which means we have to do some algebra. It means we should be able to factor the numerator as x minus 2 times something over x minus 2. And we know there has to be an x minus 2 factor on top, because if we plugged in 2 and got 0, that means x minus that number had to have been a factor. And the other factor is easy to find. X times x gives me x squared, and negative 2 times positive 6 gives me negative 12. And if we check, the middle terms do add up to what they should. Negative 2x plus 6x is 4x. Good to go. The x minus 2's cancel. So you're left with the limit as x approaches 2 of x plus 6, which is 2 plus 6, which is 8. So limit exists. And this is the place where people are like, oh, it's continuous. Oh, it's not continuous. Because the limit exists, but it's not equal to the function value. So, no, they're not equal. So f of x is not continuous at x equal to 2. Because f of 2 does not equal the limit as x approaches 2. And then to answer the original question, f of x is continuous on the interval everywhere except for 2. The negative infinity to 2 exclusive, union 2 to infinity exclusive.
Okay. So when do we do one-sided limits and when do we just get?
So I could have written this in a way that would have made you think you needed to use one-sided limits. If I had said, sure, instead of no, this one that would be stupid. Let me give you another example. Let's say we had f of x equal to, sure, let's make it really stupid, James. Yeah, let's do that. X squared, I'm gonna use the same piece up there, x squared plus 4x minus 12 over x minus 2, when x is less than 2. 2x plus 3 when x is equal to 2. And then I don't know, let's make it fun. 7x minus 6 when x is bigger than 2. So the difference between, one of the differences between this one and the previous one is this one is defined to be different pieces on the left side of 2 versus the right side of 2. Whereas, although no one would write it this way, this previous function is defined to be the same thing on the left side of 2 and the right side of 2. You could have, although again, I'll point out, you could have written this as, although everyone would be super annoyed with you if you did, x squared minus 4x minus 12 over x minus 2 when x is less than 2, 3 when x is equal to 2, and then x squared minus 4x minus 12 over x minus 2 when x is greater than 2. But since it's the same piece on the right side of 2 and the left side of 2, we don't do the one-sided limits because it's the same thing on either side. We just do the single double-sided. Over here, on the other hand, we don't have that luxury. Keep things in order, James. All right, so same deal. We're going to ask ourselves the question, well, again, where is f of x continuous? And the only place we are concerned about continuity is at x equal to 2. Because certainly 7x minus 6 is continuous everywhere it's defined. Certainly 2x plus 3 is continuous everywhere it's defined. And certainly this rational function is continuous everywhere it's defined, which is everywhere except for x equal to 2. So 2 being the place where things are changing and being the only place where this function is having division by 0 is our only candidate for discontinuity. So let's see what happens. Step 1, f of 2. So I could have made this less annoying by just saying, well, it's 7 there, because if you're defined to be the function 2x plus 3, but you're only defined to be that function when x is equal to 2, that means you just have the 1 point 2 comma 7. But I wanted to be more fun. All right, part 2. Does the limit exist? Well, now we do have to look at the one-sided limits. So the limit as x approaches 2 from the left, we're going to use this piece of the function. We already did this piece before, so I should have just factored it, but I didn't. So that's going to be the limit as x approaches 2 from the left of x plus 6 times x minus 2 over x minus 2. The x minus 2's cancel. We're left with x plus 6, which is going to be 2 plus 6, which is 8. And now we look at the other side of 2 as we approach 2 from the right. And that's going to be this piece of the function, 7x minus 6. And if we just plug in 2, we get 14 minus 6, which is 8. Does the limit exist? Yeah, the left-hand limit, the right-hand limit exists. So we can say, great. So that means these two things paired together mean the limit as x approaches 2 of f of x exists and is equal to 8. And this kind of problem is actually where people usually go wrong. Because they're like, oh, we got the left-hand limit, the right-hand limit to be the same. Things are matching up. We're good to go. But the problem is they're the same, but then there's this one point that's out of sync. Right? Our function, although I'm not going to draw it perfectly, looks, yeah, I'm really not going to draw it perfectly. Apologies for how unperfect this is going to be. It's going to look something like, I don't know, this, and then wildly steeper over here. That, whoa, geez, that's really nice, James. Okay. And that's the point 2, comma 8, but then we actually have the point 2, comma 7. So that's what's happening here, right? The limit from the right and left match up. They're both equal to 8, but then the function value was 7, so we're sad. So we can say, great, f of x is not continuous at x equal to 2. Because although the limit and the function both exist, they're not equal to each other. The limit as x approaches 2 of f of x is equal to 8, which isn't equal to 7, which is equal to the function at 2. And then we could say more generally, f of x is continuous everywhere except for 2. On the interval from negative infinity to 2, exclusive, union 2 exclusive to infinity. There's something else I wanted to mention here. No, I guess not. And then someone might say, fix it so it is continuous. And then you would say, great, I'm going to, you can cross out 2x plus 3 and either write 8, or you can write 2x plus 4, or some other annoying thing that when you plugged in 2, you got 8. Like x to the third power, that would work too, right? There's lots of things you can write there to fix it, but just writing. Okay, so in my opinion, most of the is this function continuous or not continuous at this wherever usually shows up like this. But there's another style of question people also like to ask, which, where'd you go? Kind of looks like the following, which I definitely saw at least one of your instructors do, maybe both. So we have something like, come on, paper. Yeah. Find values for the constants a and b so that the following function, f of x equal to 2x squared plus 1 when x is less than 1. And ax squared plus b when x is bigger than or equal to 1, less than or equal to 3, and 4x minus 1 when x is bigger than 3. So the f of x is continuous everywhere. If someone just says is continuous, the everywhere is implied. If I say a function is continuous, I mean it's continuous everywhere. If I say a function is discontinuous, that means it's probably continuous everywhere except for a couple points. So discontinuity just means you're not continuous at least one place. Continuous means you're continuous everywhere unless someone is more specific about it. So let's say it's continuous everywhere. So I would point out that all these functions are defined everywhere. I should say this one piecewise function is defined everywhere. Each piece is defined, right? They're all polynomials, and we're not missing any values of x. We've got all the x's less than 1. We've got all the x's between 1 and 3. We've got all the x's bigger than 3. So nothing is missing. We didn't leave anything out. Yeah. So let's do the following. So for f of x to be continuous at x equal to 1, we need f of 1 to exist, but it does. We can kind of almost skip that part, right? F of 1 is going to be a plus b. But so is the limit as x approaches 1 from that side, in this case, the right side of 1. So I would kind of skip that part and just say, what we really need is for the limit from the left and the limit from the right to do the same. So we need the limit as x approaches 1 from the left, which is going to use this 2x squared plus 1 piece. We need that to be equal to the limit as x approaches 1 from the right, which is this ax squared plus b piece. And then we can evaluate the limits easily because they're both just things we can plug in 1 for. Plugging in 1 for x, we get 2 plus 1 over here, which is 3, equal to plugging in 1 for x here, we get a times 1 plus b, which is a plus b. So we don't know what a and b are yet, right? They could literally be any combination of things to add to 3. 0 and 3, 1 and 2, -5 and 8. There's an infinite number of possibilities until we use the other piece of information, which is that the function also has to be continuous at 3. So at 3, same kind of idea. We need the limit as x approaches 3 from the left of f of x, which is going to be, if we're approaching 3 from the left side, it's going to be the ax squared plus b piece, to be equal to the limit as x approaches 3 from the right. And if x is bigger than 3, we're using the 4x minus 1 piece. And then taking those limits and setting them equal to each other, we're going to get a times 3 squared, so 9a plus b equal to 4 times 3 minus 1, which is 12 minus 1, which is 11. Now we have 2 equations and 2 unknowns. We can solve these in whatever way you're most comfortable with. I would probably, since I have, there's like, really, you could do this whatever you like. I would probably isolate b here, I guess, and say, okay, b is equal to 3 minus a, right? Taking that and rewriting it like that. And then take that and plug in 3 minus a for b right here. So the 9a plus 3 minus a is equal to 11. Simplify this, you get 9a minus a is 8a plus 3 is equal to 11. 8a is equal to 8, so a has to equal 1. Which means then b is going to equal 3 minus 1, so b is equal to 2. Sometimes there's multiple solutions to a question like this. Like a is 1 and b is 2, or a is 5 and b is 7. Like sometimes you get multiple things, but often you just get one solution. You're like, oh, a has to be this and b has to be this for this to be continuous. So usually continuity questions kind of come up in one of these 2 ways. The other thing we should mention that goes along with continuity is the intermediate value theorem, often abbreviated as the IVT. Intermediate value theorem. So here's the real gist before we draw a picture or say anything. So the idea here is that basically if a function, well, actually, let me draw something but not write words. So let's say we have this picture. Got some function. I'm going to draw it like this. The idea here is that if f of x is continuous, this picture certainly looks like it's continuous on the interval from a to b, then you should be able to get any y value between f of a and f of b somewhere between a and b. So, for example, I can get some y value, we'll call it y naught. And if I draw this line over this way, oh yeah, look, there's definitely a corresponding x value, which we usually call c, and it's between A and B, so that f of c is equal to that y value between those two y values. That's what the intermediate value theorem says. For some continuous function on an interval, if you look at the two output y values at the endpoints, you can pick any y value between those two y values and find a corresponding x value between A and B, so that that x value gives an output of that y. That's what the intermediate value theorem says. You get all the y values in between the two y values. Here are the words that go along with this theorem. So it says, if f of x is continuous on the interval from A to B, inclusive of the endpoints, then f of x takes on or attains every y value between f of A and f of B. This is kind of the more wordy way of writing it. The more mathematical way of writing this theorem is for f of x continuous on the interval from A to B, if f of A is less than y naught is less than f of B, then there must exist a number c between A and B such that f of c is equal to y naught, which again is what the picture is showing, right? F of x is continuous. We're saying there's a y naught between f of A and f of B. There has to be a number c, so that if you plug in c, you get y naught out, and c has to live between A and B. Why do we care about this theorem? Well, because it allows us to do some things, like show that some equations have solutions, even if we can't find the solution. Let's look at two examples. That is mostly what the intermediate value theorem is used for, is to show that a solution an equation has a solution, even though we probably can't actually find it. So here's one example. Show that x cubed plus x minus 7 equal to 0 has a solution. And somewhat unkindly, I didn't tell you on what interval. Deal with it. That means you get to pick. What that really means is you want to find values of x that make this function less than the number it's trying to be equal to and bigger than the number it's trying to be equal to. Also, that number there should always be 0. If not 0, make it so it is. Like, for example, I could have started off by saying, show that x cubed plus x equal to 7 has a solution. And you'd be like, great, I'm going to change it to showing that x cubed plus x minus 7 equal to 0 has a solution, because that's easier to deal with. It's always a good idea to say the function is the thing we're dealing with. So we're going to let f of x equal x cubed plus x minus 7. Pick any number that's easy to plug in. I can think of a real good candidate. Yes, but I was going to go even smaller. I was going to go with 0. 0, 1, but they're both good candidates. There is something I'm forgetting to say, though, and it is important. So before we start plugging in numbers, even though I was getting ahead of myself, first we're going to make a note or an observation. An important thing, the hypothesis of this theorem, which says that the function has to be what? Has to be continuous. Right? If you have a function that's jumping all over the place, you're not guaranteed to get the y value. You have to have continuity for this theorem to be applicable. So note that f of x is continuous everywhere. How do we know that? It's a polynomial. That's all you need to say, right? Like no one's gonna be like, how do you know a polynomial? No one's gonna question your knowledge of polynomials. It's gonna be like, great, you said it's a polynomial, you know it's continuous. Then we're gonna start plugging in values. So I'm gonna say f of 0 is 0 plus 0 minus 7, which is -7. And then let's try 1. F of 1 is 1 plus 1, up, still negative. Let's try 2. F of 2 is 8 plus 2 minus 7, which is 3. Cool. It doesn't really matter how small your interval is, but if you're trying to actually kind of narrow down where the solution is, it's kind of nice to pick the numbers that are closest to each other that gave you a positive and a negative. Here's what we're going for. F of 1 is negative. F of 2 is positive. Graphically, here's what this looks like. I plugged in 1 and I got -5. I plugged in 2 and I got +3. My function that's continuous is doing something like this. And somewhere between 1 and 2, it had to cross the x-axis. There is no other choice because it's continuous. So if you can show that the function goes from being negative to being positive, it had to equal 0, as long as it was continuous by the intermediate value theorem. So then I would write some words. I would say something like, what words would I write here? So since f of x is continuous and both f of 1 is negative, f of 2 is positive, we can say that by the intermediate value theorem, which I should just abbreviate, there must be some number c. Where does c have to live? Between what two numbers? Right, between 1 and 2. Right, there's our c right there. Such that f of c is equal to 0. If you're bigger than 0 and less than 0, you have to be equal to 0 somewhere in between. And that's kind of the gist with the intermediate value theorem. Is if you're trying to show an equation has a solution, first of all, make it so that equation is equal to 0. Then try and show that that expression is both positive somewhere and negative somewhere. Let's look at one more very classic example, and that'll be it for today. So this one's seemingly nicer, but not really. Show that cosine x equal to x has a solution on the interval from 0 to 1. So, same deal. First, we're gonna rewrite it so it's something equal to 0. Doesn't matter which side you rate things to. So we're gonna say first we want to rewrite it as show that cosine x minus x equal to 0 has a solution on the 0 to 1. And we're gonna let whatever the function is, we're gonna call that f of x or g of x or whatever you like. So we're gonna say let f of x equal cosine x minus x. I do think it's important to say that you know that the thing you're dealing with is continuous. Cosine is continuous everywhere. X is continuous everywhere. Their difference is continuous everywhere. But really, you can just write it down. You can say observe or note that f of x is continuous. We actually only care that it's continuous on the given interval. Although it's fine to say it's continuous everywhere if it is. But so you might be given a question like this where the function actually isn't continuous everywhere, but it is continuous on the interval you're dealing with. Like if it was instead, say 1 over x plus 3, right? Then you would say, oh, I can't say it's continuous everywhere. I'm just going to limit myself to the interval we're dealing with. It's continuous on the interval from 0 to 1, although yes, it is continuous everywhere. Okay. Now our job is to find a value of x that makes it negative and a value of x that makes it positive. Usually we do this by plugging in the given endpoints if we are given endpoints. But, well, let's see what happens here. If we do f of 0 is cosine of 0 minus 0, which is 1 minus 0, which is 1. And f of 1? Cosine of 1 minus 1? Any of you can tell me what cosine of 1 is off the top of your head. I'd give you all the money in my wallet, which I don't have my wallet on me, so it's not really a genuine offer. But the point is, no one of you know what cosine of 1 is off the top of your head. I don't know what cosine of 1 is. I have no idea. I have a vague idea. It's probably, oh yeah, what is it? It's probably close to 1/2, probably-ish. Because 1 radian is closest to 60 degrees, and cosine of 60 degrees is closest to 1/2. But the point is, it's not something we are good at evaluating without a calculator. So you can go one of two ways. You can either say, well, I do know that cosine of 1 isn't equal to 1. And 1 is the biggest cosine it can be. So this has to be less than 1 minus 1, which is 0. But the other way to go, which I think is the more kind of typical way to go, is say, well, I'm going to go lesser. Instead of going all the way to, say, 0 to 1, I'm going to pick a value of x that's less than 1 that I know how to take a trig function of. Pi over 3 is too big, because pi is bigger than 3. Pi over 3 lives like right there. But pi over 4 is smaller than 1. So let's try pi over 4 instead. So f of pi over 4 is cosine of pi over 4 minus pi over 4. Cosine of pi over 4 is root 2 over 2 minus pi over 4. That's 2 root 2 over 2 over 4 minus pi over 4. So I have 2 times the square root of 2 minus pi, all divided by 4. Okay, what's bigger, pi or 2 times the square root of 2? Well, pi is about how much? 3 point whatever. People know digits. 3.14. Okay. How much is the square root of 2 about? 1 point. We do need to know that second digit. It's 1.4 approximately. And 2 times 1.4 is about 2.8, which is definitely smaller than 3, which is definitely smaller than pi. You can get there without a calculator, but you do have to know approximately what the square root of 2 is. So this is definitely less than 0, definitely negative. So that means great. We've shown that the function is negative at pi over 4 and positive at 0. So we can say somewhere between, I should write all the words here. So since f of x is continuous on the interval from 0 to 1, and we saw that f of 0 is positive and f of pi over 4 is negative, by the intermediate value theorem, there must be a number c between 0 and pi over 4 such that f of c is equal to 0. Or in other words, or cosine of that number c is equal to c. Which shows that there is a solution. We just don't know what it is. Right? We do not know the solution to this equation. It's some number between 0 and pi over 4, but there's a lot of numbers between 0 and pi over 4. You can certainly graph them both and kind of see where you get the solution. You get an approximate answer, but we can't really get an exact answer. Yeah.
So if we know that cosine x minus x equals 0 is continuous for like in the entire
I would say cosine x minus x. The function is continuous everywhere. Yeah.
Oh yeah, it's continuous everywhere. With that in mind, don't we already know that there is going to be a solution?
Definitely not. There are plenty of functions that are continuous everywhere that never equal 0. Think about x squared plus 1, right? Parabola, continuous everywhere, definitely not equal to 0. So to show something's equal to something else, and if we can't actually just find the solution, we can show there is one by using the intermediate value theorem, as long as there is one. right? There actually has to be a solution for their defined shows. All right, that is it for today. I have office hours over in CADS. See y'all next week.